So last class we have discussed about the mode of oscillation of a reflex klystron. Today we are going to discuss about how to calculate the RF output power and what are the features behind this calculation and what are the parameters are going to be used to calculate the RF power output. So yesterday I have discussed a few parameters such as velocity modulation, then debunching parameter is there, beam coupling coefficient is there, then we can determine the transit time, then after determination of transit time we will identify the RF current, and once this RF current is known we can determine the RF output power, and once this RF output power is known we can measure the efficiency of a particular reflex klystron. Okay, so step by step we will see. So first one is velocity modulation. Let me check whether it is visible or not. Yes, it is fine. So velocity modulation. Now velocity modulation means what? As I have discussed yesterday, when the electrons are moving from the cavity gap, and in that cavity gap DC beam voltage is provided to it. Okay, and the DC beam voltage is sinusoidal in nature. Okay, and when it will encounter when the electron encounters the positive half cycle of a DC beam voltage, then the velocity of an electron increases. That we are going to discuss today. How it increases, how it will decrease, and what will happen at the point B, what will happen at point C. And at a time all the electrons are bunched together and disseminate in a cavity when the 3/4 of a positive half cycle of a DC beam voltage is encountered. So this is the 3/4 one, then 1/3/4, then 2/3/4, then 4/4, like that. The n number of modes are identified. So number of modes, as I have written, I have not erased this one. This will help us to calculate what are the features behind the velocity modulation. But before entering to this velocity modulation, there are few assumptions are there. First assumption is the repeller space do not affected by the RF signals. That is the first one. It should be free from the RF signal. No RF signal can penetrate to the repeller part. It will be within the cavity only. Okay. Second, the cavity gap, that is small d, which remain constant for a certain time period for the measurement of that bunching of electrons. It should not vary. It should remain constant. Then no RF field excited in the repeller space, and no no debunching must be takes place in a repeller space. These are the certain assumption to be taken before calculating the velocity modulations. Okay, so before entering to the velocity modulation, we have a small relations. That relation will help us to determine at which particular time period what are the velocity or what are the parameters are going to be used. That will help. So first, as we know that electrons are moving with a kinetic energy. Kinetic energy means it is half mv square. Now half mv square is a kinetic energy. Now this kinetic energy, how we can relate with respect to energy content when it is dissipated. So I will write it is electron volt, E. Okay, small e into capital, electric field with electron volt. Now depend upon these particular values, our parameters are half mv square and E into V. So this thing I can write, so V, or you can take as U, So it is V square is equals to twice E into capital E divided by M. So V is equals to root over of twice E divided by M. So this is the velocity relation with respect to the electronic charge, electric field, and M is the mass of an electron. So if I am going to substitute all this value, now what is E? E is the electric field. Now how this electric field is going to be measured, that also we have reason. Now there is a cavity like this, and in between that gap grid is also there, as well as small cavity gap is there. In our reflex klystron we have seen, and here the electron beams were projected like this, and these electron beams were entering to the cavity. That thing we have discussed in the last class. So there are two basic potentials are available. Two basic potentials are available. One is VR, and one, this is repeller potential. One is DC beam voltage, and one the cavity gap potential, that is called DC beam voltage. So these two potential, if I will add and divided by the repeller space, that is L, what we have drawn in the last class, then the total potential VR plus V naught divided by L, it will reveal as electric field intensity. This relation also we are going to see, but for the time being you just understand that electric fields are basically a relation of potential with respect to a distance. So potential, how many potentials are there in that configurations? In mechanism what we have seen, one is DC beam voltage, one is repeller voltage, okay, and the cavity gap potential. So these are the certain potential which we are going to use. Okay, so here I have written few relations after the assumption. First assumption is what? The RF signal may not be exist in a repeller region. That is first. Second, the RF potential must be within the cavity. It should not go out of the cavity. From that cavity only we are going to extract the energy, that is called RF output. Now what is the RF output, how it is generated? Due to the kinetic energy dissipation of an electron beams when it is projected from cathode to anode. Done. Now these are the certain, and one more assumption is that the DC beam potential is greater than your RF potential. RF potential means it is available in that cavity. The cavity itself is called as an anode. Anode is provided with a certain potential, positive potential V1, okay, that we have seen in that mechanism figure. So that V1 must be very less as compared to the DC beam potential. DC beam potential we have considered V0. So we will, with the help of those assumptions, the derivation what I am going to show you, and we will derive all these things with respect to time also. First, so as you can see here I have written V0 is very greater than V1. So that means DC beam voltage is greater than your RF potential. Done. So why we are taking RF potential as less? Because we need to increase the frequency component. Frequency component is high means wavelength is less. Wavelength is less means potential requirement must be less. Okay. Now at initial time period, suppose at t is equals to 0. In that figure we have seen, in this figure you can see the T0 is the electron without any sort of modulation releasing its energy at the 3/4 of a positive half cycle of a DC beam potential. So this is the time period T0. Now total time period capital T is a one complete cycle, that is the RF frequency you can identify. This T what I have written, it is a resonating time period, means it is the RF time period. and for a particular clock cycle these are the electrons which are going to be encountered. Now what is the relationship between T naught and capital T? This relation already we have discussed. It indicates the number of modes, and if the number of modes are going to increase, the RF output power is going to be less. So maximum power is available when the number of mode is less. Okay. Now the same thing I am discussing here with respect to velocity. Now I need to represent the potential of an electron in terms of velocity. How that potential is going to change the flow of electron. So first flow of electron need to be identified with the velocity term. So as the electrons are moving with the kinetic energy, okay, so kinetic energy is half mv square, but what is it? It's energy, electron volt. So here I have written E into V naught. E into capital E also you can write, that is the energy content, or E into V naught is equals to half mv square. Now this V square is nothing but a velocity. We need to modulate this velocity. How it is related with respect to velocity? If you rearrange it, you can see that U is directly proportional to the root over of V naught. V naught is the DC beam voltage. So at T is equals to 0, let my velocity is also U naught, which is equals to root over of 2E V naught by M. If you solve this, if I will give the electron value E as 1.6 into 10 to the power minus 19 coulomb, then mass of an electron you can consider 8.823 into 10 to the power minus 23, whatever the values are given. If you substitute it and solve it, you will get 5.93 into 10 to the power 5 root over of V naught, because the DC beam voltage we do not know. This is the only the parameter which we are going to change. Now if you change this V naught, your velocity is definitely going to change. So this is called as a velocity modulation. Well, how this velocity, initial velocity is U naught, but if you change the DC beam voltage, as you can see that U naught is directly proportional to root over of V naught. So if the V naught value is changed, your velocity is also going to change. So that means our reflex klystron is also called as a voltage controlled oscillator. It controls with the help of a voltage. If I will change the potential, if I will change the voltage, the velocity is going to change. So this is called velocity modulation, and for this reason it is also called as a voltage controlled oscillator. Okay. Now once this velocity is done, next we need to identify this potential. How this potential is going to change? This is only with respect to the initial time period, but since as the electrons are moving from cathode to anode, the time period will change. So if with respect to time period, what are the changes will happen with respect to this velocity, that we are going to discuss. So as you can see, let RF voltage at the cavity, that cavity gap D, small d we have seen. So cavity gap, the RF voltage is provided as V of t with a potential V1 that we have seen. So it is a sinusoid signal. Here you can see cavity grid potential, it is a sinusoid signal. So this sinusoid signal I am writing V of t is equals to V1 sin omega t. Done. So this is called as my cavity gap potential, which is also called as RF potential. So it is V1 sin omega t. So this is the first assumption. Then next, in that gap small d, when the electrons are crossing from lower plate to the upper plate, means if the gap is like this, it will move from this point to and this point. So what is the gap? The gap is small d. Okay. Now when the electrons are crossing through this gap and return back to the cavity, for example this is only one electron I am discussing. So here what happens, the electrons is having its own velocity. Done. When it is crossing this gap, it is having the transit time, that is Tg, what we have discussed last class. So what is the relation? T is equals to d by u. Here I have written d by u naught. So Tg is equals to d by u naught. Similarly, at the same time, you can identify the transit angle. Transit angle is what? Theta g is equals to omega into Tg. Omega is the angular frequency and Tg is the gap time period. Tg is the gap time period, means the transit of electron while crossing this gap of a distance of small d with a velocity of u naught. Then t is equals to d by u naught. Theta g is the transit angle. These are the certain limitations we have discussed in conventional tube. This how this transit angle is going to be enhanced. So with this help, with the help of reflex klystron, this transit angle will be increased and at a low power, high frequency. Okay. Next, we need to calculate the total potential. So average potential first we have to calculate, because there are two different potentials are there. So first of all, we have to identify the average potential at the gap. So at average microwave voltage in a gap, what is the average microwave voltage? Because whenever we are calculating the potential, we are calculating with respect to RMS. RMS with the input, DC beam voltage with RMS value. But here it is an average value. So average, how we are calculating? 1 by T, 0 to T, V of T into dt. So that is the basic formula for an average calculation. So average calculation is V average is equals to 1 by total time period 0 to T, V of T into dt. So this is the average. Now for whom we are calculating? For the cavity gap. So for a cavity gap, what is the potential? It is the RF potential, that is V1 sin omega t. So in place of V of t, substitute V1 sin omega t. So here I have written 1 by Tg, 0 to Tg, because the electron is crossing the gap for a time period of Tg. So V1 sin omega t into dt. Now it is a simple integration. V1 is a constant, take outside. Sin omega t integration is cos omega t divided by sin omega t. Now limitation is 0 to Tg. If you substitute it, you will get V1 1 minus cos omega Tg divided by omega Tg. Done. So 1 minus cos theta means I can write 1 minus cos theta is equals to 2 sin squared theta by 2. This is the trigonometric relation. Same thing I have written here. So it is V1 sin square theta g by 2 divided by theta g by 2. Now why I have written theta g by 2? Here it is omega tg, but here I have written theta g by 2, because omega tg, as you can see, omega tg is equals to theta g. Done. So in place of theta, if you substitute omega tg, it will become as a 2 sin square, or 1 minus cos omega tg. I can write 2 sin square omega tg by 2, because angle is going to be half. So omega tg is replaced by theta g and 2 is as it is. So it is V1 1 minus cos omega tg by t omega tg, which I have written V1 sin square theta g by 2, and this one is theta g. Now upper one is 2 sin square, bring that 2 to downward, it will become as a theta g by 2, and for this particular representation I will extract one constant factor. I have written V1 beta 1 sin theta g by 2. Done. So here sin square separate, and sin square means there are two sin terms are there. 1 sin divided by theta g by 2, that is beta 1, and V average will become as a V1 beta 1 sin theta g by 2. Now this B1 is called as a beam coupling coefficient. Now here how many number of electrons are moving, that we don't know, but the beam coupling, so these beam are coupled with each other and dissipate the energy at the 3/4 of the positive half cycle of an RF signal. So this is called as a bunching. Now first of all, in the last class I have discussed there are two type of same cavity. In reflex klystron we have only one cavity and it works in a two different manner. When the electron beams are projected from cathode to anode, then it is called as a buncher cavity. But when it is in a reverse manner, means again if it is returned back to the cavity, if the electrons are repelled back to the cavity, then the cavity will act as a catcher. So here we are calculating with respect to electrons are moving towards the repeller. So here this beta 1 is called as a beam coupling coefficient. Okay, so this is the first term. Beta 1 is called as a beam coupling coefficient. So I will erase this. So here beta 1 is equals to sine theta g by 2 divided by theta g by 2. Done. So this is called as a beam coupling coefficient. Since it is a coefficient, it is a dimensionless quantity. It is a constant. Okay. Beta 1 is a constant. Beam coupling coefficient, which is a constant value. Angle by angle is a constant value. Okay. So this beta 1 I have substituted here. So our V average potential at the microwave voltage in a gap, V average is equals to V1 beta 1 sine theta g divided by 2. In some of the book it will be written in terms of omega tg by 2. In some of the book it will be written in terms of theta g by 2. Both are same. Need not to worry about it. Okay. So this is our average potential. So beta 1 we have identified as a beam coupling coefficient. Then V average is the average potential in a particular gap. Now when the electrons are moving with a uniform velocity, and when they will enter to that gap, the velocity modulation takes place. How that modulation takes place, let's see. Initially, when there is no external potential is available, only with respect to DC beam voltage, the velocity is u naught 2e v naught by m. Okay. But when the same electron enters to that gap, enters to that particular cavity, while crossing from that gap and moving towards the repeller, it will identify or it will face some sort of energy, and that energy will boost them and the velocity increases. How it will increase? Let's see with this relation. Now here you can see I have calculated velocity at t is equals to 0, initial time period. Now for a time period t, here we have identified Tg. Tg means the gap time period. The electron beams are crossing the gap for a certain time period of Tg. So u of Tg, okay, u of Tg is equals to root over of 2e by m v naught plus v average. Now why I have added v average? Because now up to this much the beam is not entered to the gap. Now if I will write u of Tg means electron is entered to the gap. If it is entering to the gap, it will face three different criteria, three different situations. One, positive half cycle of a RF signal. Second, the zero crossing point, and third one is the negative peak value in the diagram what we have seen. So maximum velocity will be given to the electron when it is encountered to the positive half cycle, and the least velocity will be given when it will encounter the negative peak potential. Okay, so here it is 2e by m v naught plus v average. So v average is the average potential which is available in that gap. So this is the value. So now you can see, if I am changing the potential, velocity is changed. Here I am changing the velocity, changing the potential. Initially it is DC beam voltage. Now I have added the average RF potential. This is average microwave potential in that gap is added to it, and so that the velocity will increase. And once this velocity increases, it is called as a velocity modulation. And one more important thing, if we are discussing about modulation, we have a modulation index also. That modulation index will govern that which type of modulation takes place. Okay, so let's see. So in place of V average, I will substitute V1 beta 1 sine theta g by 2. Step by step, it is a very easy one. Let's see. 2e by m. Take V naught as a common, whole into 1 plus V average divided by V naught. Okay. Now what is this root over of 2e V naught into m? It is nothing but initial value, initial velocity. So I will write u naught root over of 1 plus, in place of V average I will write V1 beta 1 sine theta g by 2 whole divided by V naught. Done. Okay. Now here this parameter, this one V1 beta 1 by V naught, this V1 beta 1 by V naught is called as depth of modulation, depth of modulation, or you can say degree of modulation, degree of modulation, or we can say it is called modulation index. Okay, it is called modulation index because here you can see DC beam voltage is greater than the RF. Done. So DC beam voltage, if I will compare with respect to AM signal, how we are determining that our modulation index, it is the maximum amplitude of a message component divided by the maximum amplitude available in the carrier component. So that will reveal the modulation index. Similarly, here V1 beta 1 divided by V naught, this ratio is called as degree of modulation or depth of modulation or modulation index. So this is the basic criteria through which we can identify our modulation index, and we can say yes, modulation happens. Which sort of modulation? It is a velocity modulation. So here I will write in a neat manner u of tg u naught 1 plus v1 beta 1 divided by v naught sine theta g divided by 2 whole to the power half. Done. Now if you expand this with the help of some Fourier expansion, Fourier series, so this half will come down, so we will get u naught 1 plus v1 beta 1 2 v naught sine of theta g by 2. It is a simple expansion. Means 1 plus x whole to the power half, this I can write 1 plus x by 2 plus dot dot dot. Some higher components are there. I am neglecting that higher component. I am only considering this particular factor. So here I have written u naught 1 plus v1 beta 1 divided by 2 v naught sine theta g by 2. Now what is our modulation index? Modulation index is v1 beta 1 divided by v naught. Done. So the above equation can also be written as u of tg is equals to u naught 1 plus v1 beta 1 divided by 2 v naught sine of this theta g, I can write omega tg minus theta g by 2 in this form also I can write the equation, because many of the books they will write in this particular manner or in this particular manner. Both are same. Why? Because as we have written, omega Tg is theta g. Done. So theta g minus theta g by 2 is equals to theta g by 2. Same thing I have written here. Done. So this is my velocity modulation. So velocity modulation with respect to what? With respect to potential. Whose potential? First is DC beam voltage, second the RF voltage. Done. So this is with respect to the gap time period, and this is the velocity what the electron encounters when it is crossing through that cavity gap. Done. Next we will discuss about the transit time. Okay. So next one is our transit time. Done. Transit time means when the electrons is crossing from the gap and again return back to the gap. So that means twice. So twice we have to calculate. So twice we have to take as a twice of the velocity. So when the electron is crossing this gap, let us consider this gap is a cavity gap is a small d. So first of all, the electrons are crossing with a velocity and again it is returning back to the same cavity. So that means twice the velocity we have to consider, divided by the particular acceleration of an electron, and that acceleration is given with respect to the accelerating grid. So here the transit time, as I have written, it is twice the velocity divided by the acceleration, or you can say it is twice of the velocity by acceleration, twice, because once it will cross and again come into the same gap. So it is to and fro we have to calculate. So to and fro both, it is twice. So velocity by acceleration of an electron. Done. For that, what are the things we have to consider? First, the transit time, or the transit time depends upon velocity and acceleration. So first of all, you need to calculate the acceleration, because velocity already we have calculated, that is u of Tg is equals to u naught 1 plus beta v1 beta 1 divided by 2 v naught sine of omega Tg minus theta g by 2. But here only one unknown factor is what? Acceleration. How to identify the acceleration? Acceleration is identified with the help of a principle. Suppose this is an electron, for example, or an object, let us consider. If I will put a force on it, so what will happen? It will move in this particular direction with a certain acceleration. So m into a is equals to f. Done. Now m into a means it is an object. Now here it is an electron. We are giving a force on an electron. So that force is, electronic force is Q into E. As we have studied in our field theory, the force exerted on an electric field by an electric field on a charge is Q into E. Now Q into E is equals to m into a, mass into acceleration, because electron will have certain mass and it is moving with a certain acceleration. So acceleration I can identify as Q into E divided by m. So this is a small relation. So Q is nothing but an electronic charge that is represented by E. So here I have written A is equals to small e into capital E divided by m. Small e is the charge of an electron and capital E is the electric field which is exerting on a particular charge, and m is the mass of an electron. Done. Now here E by m is a constant value, but what is the E? E is the electric field. Electric field, where it exists? Electric field between the cathode and the anode, and more about the repeller also, because the repeller gap we have to consider. Okay. So here V naught plus Vr plus V1 sine omega t divided by L. L is the repeller gap. that cavity to repeller, it is having a certain gap, what I have shown in the earlier class as L. L is the distance. So what is the total potential available in that reflex klystron? First, DC beam voltage is V0. Then next, repeller is also available, repeller potential VR, and one DC beam potential is given to the cavity. Okay, given to the cavity RF value. So RF potential is V1 sin omega t, and we have considered that RF potential is very less as compared to repeller potential and the DC beam voltage. So I am neglecting this V1 sin omega t, and what is the distance? Distance is L. So this will be L. Electric field will exist in that particular region. Done. Now if I am neglecting V1 sin omega t as a very small component, I will get acceleration is equals to E by m V0 plus VR divided by L. This component I have suppressed. Why? Because the value is very less. Next. Now this is my acceleration. This is my velocity. Substitute in this equation. I have substituted. So transit time Tr is equals to twice of u of Tg by A. In place of u of Tg, whatever the details we have got from this relation, substitute here. A is value is this, substitute here. So it is only need to substitute, nothing else. Same equations are there. Only you have to substitute the value. So what we have identified, twice of u naught ml 1 plus beta 1 v1 2 v naught sin theta g by 2 divided by E v naught plus r. So E v naught plus r, this L and M move upward. Done. Now here this is the at particular Tg, the time period whatever the transit time we have calculated at a Tg. Now similarly we can calculate for an initial time period at T. How? T can be initial time period means at a point B where there is no velocity modulation takes place. So here you can see at T naught I will write 2 u naught by A. So 2 u naught by A means in place of A substitute this value, acceleration E by m v naught plus vr by L. So this I have substituted. Now this value is little bit available here, twice of u naught ml divided by E into v naught plus vr. So this whole term I can write as T naught. Done. So that Tr is equals to T naught 1 plus beta 1 v1 divided by 2 v naught sin omega tg minus theta g by 2. So this is a simple relation. Now T naught is equals to nt. We have formed a relation that T naught, that a small time period T naught is equals to capital N into T, where capital N is n plus 3 by 4 into capital T. Number of modes, same thing I have substituted here. So T is replaced by 2 pi by omega, and N represented as a number of oscillations, number of modes are there. If the number of modes are increasing, your RF output is less. To identify the maximum RF output, the mode of oscillation must be less. Okay, so these are the basic relations. So here you can see the transit time we have represented in terms of T naught. Done. In terms of velocity modulation technique, it is also done. We have represented this one in terms of degree of modulation. Degree of modulation is what? Beta 1 V1 divided by V naught. Okay. So this equation is called as for transit time. We have seen velocity modulated signal, how the velocity modulated signal is happening, what are the velocity modulation, how it is happened, what are the potential are going to come into picture, how we have calculated to find out the velocity modulated of electron, or you can say electrons are velocity modulated for a certain potential. Similarly, transit time is also come into picture with respect to this velocity modulation. So velocity modulation means when the electrons are crossing to the particular gap. When it is entering to the gap, it is automatically velocity will enhance. With the help of this sort of relation you can understand. Before the gap, it is only having the DC beam voltage. But when it is entering to that gap, the RF potential is going to add it to it. Then what happens? Then velocity of an electron increases. And if it is increases and if it is decreases, that means if there is a variation in a velocity, then we can say it is called velocity modulation. And who will govern this modulation index? Degree of modulation, depth of modulation, and modulation index. So this is my modulation index. Okay. Using the same thing we have derived for transit time. There are other parameters are there that we are going to discuss now. Okay. So this is density modulation and beam current. So up to transit time we have calculated all those relations. Velocity modulation also we have calculated. Now, as I have discussed earlier, after determination of velocity modulation, next we have to determine the transit time, and then we have to go for the calculation for the beam current and the RF current. Okay. Once the RF current is known, RF potential is available, you can determine the RF output power. DC beam current is available, DC beam voltage is available. Multiply these two, you will get the DC power, and at last we can determine the efficiency by taking the ratio of RF output power by the DC input voltage into 100. So that is the simple calculation. But to reach that calculation, these are the certain steps. So bunching parameter is also we have seen. Now we will calculate all those things with respect to the bunch of electrons. Now when the electrons are moving from cavity gap, it is in a form of a bunch. As I have told, when it is in forward condition, the same cavity will work as a buncher. But when the same electrons will return back to the same cavity at the same time, it will act as a catcher. Okay. So now here we are discussing about the bunching. So bunching means beam current we have to identify first. Once this beam current is known, easily we can determine the RF current. Okay. So how to determine that beam current? Let's see. I have written few expressions. I will explain one by one in a precise manner. So first, it is called density modulation and beam current. Density modulation means that how that particular bunch of electrons are going to generate a particular beam current. Okay. First, time of arrival of electron to the cavity gap. Now, first the thing is we have to calculate the total time period. First, we have calculated initial time period T naught. Then next we have calculated the gap time period, that is Tg. Then third we have calculated transit time period Tr. Next we have to calculate the return back time period. Return back time period to the cavity, that it is represented as a Tb. So Tb is nothing but gap time period plus transit time plus transit time Tr. So it is Tg plus Tr. Tr is what? Tr is already we have calculated. So in place of Tr I have written T naught 1 plus beta 1 V1 2 beta naught 2 V naught sin theta g of t plus Tg. Tg is the gap time period, Tr is the transit time. Okay. Now if you expand it, this T naught, as we know that capital N into T, T naught is equals to capital N into T. This I can write 2 pi N divided by omega. Same thing I have written. T naught, if you multiply with 1, you will get 2 pi N by omega. Directly I have written. Then the same 2 pi N by omega multiply with these constant coefficients. If you multiply, you will get pi by N. 2 will be cancelled out. Beta 1 V1 V0 sine of this. Okay. Now make this whole equation into a simplified manner. This particular term pi N beta 1 V1 divided by V0 is called as X. This is called as a bunching parameter for a reflex klystron. It remains constant. It is a constant value because DC beam voltage, what you are providing is a constant. V1 is the RF potential, which is also constant. pi is a constant value, n is the number of modes. If the number of modes are increasing, your bunching parameter will decrease. This is the bunching parameter will increase. If the bunch parameter increases, what will happen? The bunching parameter increases means output power is very less. Why? Because if the number of modes are increasing, output RF power is less. That relation also we have discussed earlier. And beta 1 is the beam coupling coefficient. That beta 1 we have seen what is the constant value. Beta 1 what it is? Beta 1 is equals to how much? Beta 1 is a ratio of sine of theta g by 2 divided by theta g by 2. So this is the beam coupling coefficient. This is the bunching parameter. So substituting x here. So my equation will become Tb is equals to Tg plus 2 pi by n by omega plus x by omega sine theta g by 2 over. So this is called as a time period, beam time period. Now once this time period is known, I will determine the beam current. So we have, so Tb is depend upon Tg. So if I will differentiate this equation and multiply with the DC current, then I will get this relation. How? If I will differentiate dTb with respect to dTg, you will get differentiation with respect to Tg, it will become 1. This is a constant value which is 0. Here it is x by omega and here it is sine of omega Tg. So this theta g you can replace by omega Tg minus theta g by 2. If you differentiate it, this sine will become in terms of cos. So cos of omega Tg minus theta g by 2. So omega will come outside and omega and this omega will be cancelled out. So resultant we will get as 1 plus x cos omega Tg minus theta g by 2. So this is the ratio. Now how I have identified this particular differentiation? The answer is when the bunch of electron return, when the bunch of electron which is crossing to the gap and return back to the cavity, then the total current is called as a beam current. Okay, the total current is called as a beam current, and we have a relation I naught into dTg. I naught means it is a DC beam current into dTg is equals to beam current into dTb. So this is a relation, simple relation. So here the total current must be equal. So I naught into dTg is equals to IB into dTb. So dTb is what? It is a differentiation of this. So if you rearrange this equation, we will get beam current IB is equals to I naught, which is DC current, dTg divided by dTb. Only substitute this value with respect to I naught, you will get your beam current, DC beam current. So IB is the bunch beam current. This is the constituent of the beam current. Bunch of electron return constitute to the beam current. So I naught is a DC beam current, IB is the beam current at the returning to the particular cavity. Now once this IB is known, you can expand it with the help of certain expansion. What sort of expansion? Binomial expansion. So when I will expand this minus 1 in a binomial expansion, 1 plus x to the power minus 1, I will get in terms of Bessel functions. Okay. So here I have, for simplification I have written here. So it is IB is equals to I naught plus 2 I naught summation n equals to 1 to infinity Jn of nx cos omega Tb minus 2 pi n minus theta g by 2. So these are the fundamental equations, standard equations. Here only we have to identify the mode for n is equals to 1, or if you substitute n is equals to 0 means it will not consider. N equals to 1 means real value. If it is n equals to 0 means only the DC beam current is going to identify twice of I naught. If I will take this one inside, here I will put n equals to 0. If n equals to 0 means this whole value will come. Okay. So IB is equals to I naught plus 2 I naught, n equals to 1 to infinity Jn of nx cos n omega TV minus 2 pi n minus theta j by 2. And this equation we have identified with the help of an assumption what? My RF's potential is less than the DC beam voltage and my bunching parameter must be very less than 1. This parameter must be very less than 1. Very less than 1 means what? The number of mode is very less. Okay, your DC beam potential is must be very greater than with respect to this RF potential. Then only the X value will come as less than 1. So these are the certain assumptions to find out the exact RF current. So here IRF is equals to the fundamental component if I will identify. So it is beta 1 twice of I naught J1 of X cos of omega TV minus T0 minus Tg by 2. And IRF is equals to rearrange this particular function. This is the negligible part. You can neglect it and you will write IRF is equals to twice I naught beta 1 J1 of X cos of omega TV minus 2 pi n. So this is the resultant of RF current. RF current is identified in the particular cavity gap, in which all the bunch of electrons are repelled back to the cavity, release their energy in the form of kinetic energy is converted into the form of RF energy. And if the electrons are moving, the current must be there. And this RF current is measured within that particular cavity, not in repeller side, within the cavity. So this is called as our IRF. So once IRF is known, we can determine the RF output power. Once RF output power is known, efficiency can be identified easily. Okay. So this is the RF current, and with the help of this RF current we can easily calculate the RF output power. So here you can see that RF output power is calculated only with respect to the magnitude part. So here we have written IRF is equals to twice I naught beta 1 J1 of X cos of this. So take the magnitude part. This is our magnitude part. Beta 1 is the beam coupling coefficient. J1 of X is the first Bessel function with respect to the bunching factor. RMS power B1 into IRF by 2. V1 means it is the RF potential what we are providing to the cavity gap, and IRF by 2 is the total current. So substitute this value. If I will substitute this value here, I will get V1 beta 1 I naught J1 of X. Done. Now V1 by V naught, if you divide it, you will get twice of X divided by beta 1 2 pi n. We can write as X divided by beta 1 pi into n. So these are the small relations are there. Okay, but our target is to determine the RF output power. So PRF is equals to V naught I naught X J1 of X divided by pi n. So this is my RF output power. So RF output power is determined with the help of these above two relations. So here it is V naught I naught X J1 of X divided by pi n. But what is this pi n? That also we have seen, the twice of root over of 2e V naught by m into ml divided by e into V naught plus Vr is equals to 2 pi n by omega, or you can write nt. For simplification, this is my RF output power. Done. So what is my DC power? DC power is V naught into I naught. Take this component down, you will get your efficiency. So efficiency is X J1 of X divided by pi n. X J1 of X divided by pi n. That is the efficiency of a reflex klystron. And RF output power can be written in terms of V naught I naught X J1 of X V naught plus Vr divided by 2 pi f into L, or you can write omega into L. L is the repeller length root over of E by 2m V0. So this is the calculation for RF output power and efficiency. Once these two parameters are known, that means it is easy to justify what is the RF power we are going to identify. The RF power, you can see, it depends upon DC potential, DC current, bunching factor, beam coupling coefficient, frequency, repeller length, velocity, potential, everything. It depends upon all these things. So RF power basically taken out from the cavity, and reflex klystron is having only one cavity. Once again I am telling, the cavity will work in two manner. When the electron beams are moving forward, at that time it will act as a buncher cavity. But when the same electrons which are repelled back to this same cavity, then it is called as a catcher cavity. Okay. So these are the simple relations are there. Go through this relation. Next class we will discuss few numericals with respect to the reflex klystron and number of modes, how we are identifying all these values. Okay. For the time being, thank you all.